Hey there guys, AlphaKoala here, doing a bit of an introduction to statics, and we're going to be looking at pulleys. Pulleys. Alright, now, a lot of people seem to be having problems with pulleys. So we're going to go over a couple of examples and show you how the forces kind of interact. The first example will just be a simple pulley with a string going over it. For the purpose of this, we're going to assume that all pulleys will in fact be frictionless. And it's got two masses attached to springs, right? This has got a weight of 100 newtons, and we don't know what this object's weight is. Now, we're given in this scenario that this object is going to be at an equilibrium. Now, what do we know about an equilibrium? That means that this box, if we draw a free body diagram over here, if it's got 100 newtons acting down on it, it's going to have 100 newtons acting up at it, because the total of the forces should be equal to 0. Alright? So we know, from our free body diagram, we rub that out, that this string must be pulling this way at 100 newtons. So it's going to have a magnitude of 100 newtons. So let's just put that in there. Alright, that's 100 newtons. So if this string's being pulled 100 newtons, the only thing pulling the string down would be this weight here. So then this weight will have to be 100 newtons. Which kind of makes sense at an intuitive level, you know, they're kind of balanced, so, you know, if they're at an equilibrium, their weights are going to have to be equal. Otherwise, you know, if one object was heavier than the other, it would be moving down and vice versa. So the fact that they're in equilibrium, you know, kind of shows that they're going to be the same weight. Now this wouldn't matter, of course, you know, we could kind of rub this out and we could draw the weight up here. And as long as they're still in equilibrium, those forces will always be equal. Alright, so that's kind of a brief look into a fairly easy example. Okay, so let's go into something a little bit more complex. Okay, so this example, we're going to have a pulley. It's a fixed pulley. And it's got a weight that's supposed to be a straight line of 100 newtons. Alright, and it kind of connects to another object at, you know, an angle. We'll call that 60 degrees. And we'll just draw a little thing. And that's a fixed point there. Okay, so basically there's a string attached to a fixed point, going over a pulley, attached to a weight, and, you know, it's all in an equilibrium. So, basically what the question is going to be asking you is to find out the force that is acting on this fixed point. Now, we know that if this weight is pulling down at 100 newtons, this rope's going to be pulling, you know, that way at 100 newtons, right? So, for this object here, this point, to not be moving, it has to be pulling in the opposite direction at 100 newtons, because that is actually Newton's first law. Oh god, that was a bad pun. So basically, Newton said that the newtons in each direction are going to have to be equal, and that's really painful to say. So, you know, if that's pulling 100 newtons, then we know that the force pulling on the other side is also going to be 100 newtons. So this is pulling 100 newtons this way, which is going to be pulling that up 100 newtons, which would balance out its weight. So that kind of makes sense, right? So if we draw the free body again, if that's going 100 newtons down, it's going to have 100 newtons up, which means that this has to be pulling 100 newtons that way, which is that way. So, because tension in a rope is going to pull the rope both up and down. Like, there's no set direction. It's kind of going both ways for, you know, any kind of situation. Okay, so we've got that this is going to be going down 100 newtons at an angle of 60 degrees. Now, we know from this, we can just kind of rearrange to get hypotenuse, sine, theta will equal opposite, and hypotenuse, cos, theta will equal adjacent. And that will give us these two values, and from there we can kind of work out the forces that are acting on that. But that brings us to our next question. What force is acting on the pulley? So to go over that, we're going to quickly go back to our first scenario, where we got a pulley, and we got, you know, a string kind of going that with two weights, both acting down at 100 newtons, right? Okay, so you would kind of look at that and say, you know, if you got a string over a point with, you know, hanging 100 newtons or 100 kgs, but it's 100 newtons, of, you know, a fixed point, that's going to be pulling down at 200 newtons. And that would be exactly right. So the force on the pulley will actually be equal to, you know, 100 newtons plus another 100 newtons, which all up is going to be 200 newtons. And that's going to be acting in the same direction as the forces are. So to keep that in place, if we draw a free body for it, oops, I'll actually just put that back in. Alright, so we draw a free body diagram for the pulley. If it's going down at 200 newtons, then to stay in equilibrium, it must be getting pulled up at 200 newtons. So the force required to keep this pulley at equilibrium is going to equal 200 newtons in the up direction. Alright. our example, we got a pulley here, and we gotta be running just a strand of rope here again, 100 newtons. Keep the numbers nice and easy. And this time we're gonna be running it at an angle. And, that's gonna have two directions, that way and that way. So, let's just put this, I don't know, it's 45 degrees. That's gonna be 100 newtons, as we proved before. So, if that's gonna kind of count that, it's gonna be pulling 100 newtons. Alright, so if we just put that into our calculator, we get 100 times sine 45 to get the opposite, which is going to be 70.7 newtons. That's going to be going down, and 70.7 newtons in the adjacent direction. Okay, so now we can see that we've got three forces acting on the pulley. We've got a force of 100 newtons acting down. We've got a force of 70.7 newtons acting down. And we've got a force of 70.7 newtons acting across. So, if the force, on the pulley, by all these objects, is going that way, then to keep it in equilibrium, we need an opposite force going in the opposite direction. An equal force going in the opposite direction. So we just change this arrow to the opposite direction. And that will be the force required to keep the pulley at equilibrium state. And using Pythagoras' theorem, we can kind of work out this angle, and it's going to be 100 newtons because that shows really good numbers, and we know that's going to be 45. No, sorry, actually. Sorry, I got a little bit ahead of myself. Sorry. No, actually. Because you actually have to plus these two vectors, because, 100 newtons that way plus the 70 newtons that way, that's actually going to be 170.7 newtons. And that's just the resultant of the 100 newton force acting downwards on the pulley and the 70.7 newton force acting downward on the pulley. Okay, so from the Pythagoras theorem, we can work out that 70.7, squared plus 170.7 squared, and then we square root the whole thing, and we're going to get, if I can get my pen lit up, 184.76 newtons acting that way. And how are we going to find our angle? Well, we can kind of just use basic trigonometry for that. So we'll just use our tan inverse, and our tan inverse is going to be opposite over adjacent. So that's going to be 170.7, if I didn't enter that in right, and that's going to be divided by 70.7. See, that's just opposite over adjacent. And we'll actually just write that out. So we know from our identity that tan theta equals opposite over adjacent. So that the theta, the angle, is going to equal tan negative 1 opposite over adjacent. So theta is going to equal 170, the tan inverse of 170 divided by 70.7. And that will give us an answer of 67.5 degrees. So we know our angle now. Okay, so basically your answer would be the required force to keep the pulley at an equilibrium would be 184.76 newtons at 67.5 degrees in the 67.5 degrees from the horizontal plane. You could also have just as easily gone, well, if there's 170.7 newton force acting downwards on the pulley, there must be a 170.7 newton force acting upwards to counter that. And if there's a 70.7 newton force acting that way, you could say there's a 70.7 newton force acting that way. And as we know, that way is just going to be 70.7i, that was going to be 7.7j. And you could have answered in a Cartesian form, such as 70.7 newtons, 170.7 newtons. And if you don't know how to do Cartesian forms or something, you should probably look that over because we're going to be using that quite a lot. Okay, so that's just a basic kind of introduction to how pulleys work, and hopefully from that everyone can kind of go do their own research and get a thorough understanding on it. Thank you for watching, and look forward to my next video.